Hi, everybody. Mr. Martinez here. I hope all of you are having a good day. Today's breathing exercise is how can you appreciate Mother Earth? So maybe you want to pause this video and just take a couple breaths and think about how you can appreciate Mother Earth. Announcements for today. Keep up the great work. I know that this is difficult for many of us. Just want to encourage you to continue to keep up the great work that you're doing. Next announcement is that I'm very proud of you of all the hard work that you are doing. And I have a joke. Feel free to read it. Hopefully you understand it. Hopefully you got a laugh out of it. We are going to start off class by watching this awesome video.
Sides of equal length and angles of equal measure. I'm a regular polygon. I think I'm pretty special, a geometric treasure. I'm a regular polygon. The others are irregular, and that might be their pleasure. But I'm a regular polygon with sides of equal length and angles of equal measure. I'm a regular polygon. I'm a regular polygon. I'm a regular polygon.
All right, awesome video. Just a reminder of regular, what they look like, and irregular, what they look like. So regular triangle versus an irregular triangle, regular quadrilateral versus an irregular quadrilateral, pentagon, regular, irregular, hexagon, 6 sides, regular and irregular. Today, what we are going to do is we are going to continue learning a bit more about regular polygons, specifically how to calculate the area of regular polygons. So if you missed the video where I go over the formula for regular polygons, you might want to go back to that one first. Okay, so we are going to review a couple things quickly. Remember, the main idea is that all regular polygons can be inscribed in a circle. So this pentagon in blue is inside of a circle. And in black, we have the center of the circle and also the center of the pentagon. In green, we have the radii of the circle, but it also happens to be the radii of the pentagon as well. Because notice how the pentagon touches the circle at this specific point, which makes it the radii of both the circle and the blue pentagon. Central angle, the central angle, just like circles, what we talked about, it is in between two radii. So the central angle is in purple. And the apothem is the one in red, which would be the altitude of the triangle that's formed by the two radii and the side. So, for example, this red one is the altitude or the height of this triangle created by the two radii and the side. And then this in black, if I knew where exactly the point should be for the apothem to be perpendicular, then that would be the apothem of this triangle, and so on. So we can draw an infinitely many apothem, but we won't focus on that just yet. Okay, so a little bit more about some of the questions that you might see on the homework, or some of the questions that you might encounter are the following. Similar to this one, given a regular quadrilateral, find the central angle of each triangle. Okay, we'll come back to this. Let's quickly recap the area of a regular polygon. So this is the area of a regular polygon. We have area equals perimeter, which is everything in green. So the perimeter is if you walk around the shape. Again, you walk around all the three sides of the triangle, walk around the three sides of the pentagon. And the apothem is the height of the triangle created by two radii and the side of a polygon. So I will do my best to draw the apothem for this triangle. So if I draw the two radii in black, and then I'll eyeball the apothem. So that's the apothem. And again, this hexagon has specifically 6 apothems. We just don't draw them all out, but I'm going to draw this one out here. So here's the apothem for this triangle. Now the apothems are congruent because these triangles right here are all congruent. In fact, this hexagon ends up having 6 tiny triangles because notice how we can draw 6 radii. So notice the 6 radii. Radii 1, radii 2, 3, 4, 5, 6. The same thing for, even though this is a regular triangle, we can still create triangles inside. So if I go from the center to the vertex, center to the vertex, center to the vertex, these triangles inside the equilateral triangle are all congruent. So triangle 1, 2, and 3 are all congruent, and they are inscribed inside of a circle. So if I was to draw a circle, that circle would intersect the triangle, or the vertices would intersect the triangle. So vertex 1, vertex 2, vertex 3, the vertices would cross the circle. Same thing for the hexagon, and then same thing for the pentagon. It's just we do not draw the circle always. Okay, so again, the apothem, just a reminder, is, and I'm going over it pretty slowly so that we can understand it. It is perpendicular to this side, and it starts from the center. It is perpendicular to this side, and it starts from the center. It is also perpendicular to this side, and it starts from the center. And all these 3 apothem are congruent. Because I have not constructed it, meaning it's not accurate, that's why some look a little bit longer than the others, but they should all be the same length if I had a compass and I had constructed the apothems. Okay, so again, same thing for the pentagon. So let's go back to this question. Given a regular quadrilateral, find the central angle of each inside triangle. So it's asking us to find the central angle, and you might be wondering, well, there are no central angles because central angles are usually within a circle, and you're correct. And then you might be wondering, of each inside triangle, what do you mean by that? So just taking it back again to this image. So because it's a regular quadrilateral, we talked about here, all regular polygons can be inscribed a circle. So what we're going to do is we are going to draw a circle. So this circle, notice how it's inscribed. Or sorry, this polygon is inscribed a circle. So that means that each vertex, vertex 1, vertex 2, vertex 3, and 4, are all intersecting the circle at just that point and nowhere else. Okay, so if we locate the center of the square, if we had drawn this with a compass, if we locate the center, I can draw in all 4 radii. So radii 1, 2, 3, 4. So the radii are in red, which I have drawn there. All right, so I'm going to go ahead and change them to black just so that we can, or to blue, just so that we can not confuse them with the apothem. So in blue are the radii. And notice how we have created 4 triangles. So triangle 1, 2, 3, 4. Now, let me remove the square. So I'm going to remove the square for now. So we actually have 4 central angles. Remember, a central angle of a circle is bounded between 2 radii, and the vertex of the angle is at the center of the circle. Okay, so we're trying to figure out this central angle. So the the degree from here, from that side to this side of the angle, and then also from this side to this side, and then also from this side to this side, and this side of the angle to this side of the angle. Okay, so that's what we're trying to figure out. So now we're going to bring back the square, and you can see that there are those four same central angles. So what we are going to try to do is we are going to try to figure out the measure of each central angle. Now, because this is a regular quadrilateral, we can actually figure out the measure of each central angle. And that's because this whole circle that is touching the square, and we know that this square is regular, meaning that all four sides are the same length. So side 1, side 2, side 3, side 4. And that is creating four congruent triangles, triangle 1, 2, 3, 4. These four triangles, we can actually prove that they are congruent. So because of that, we know that each central angle 1, central angle 2, central angle 3, and 4, those four are congruent. So what we are going to do is we are going to take the measure of the whole arc of the circle. Remember, the whole arc is 360 degrees. So we're going to do 360 divided by 4. And we are going to divide it by 4 because we have 4 congruent central angles. So divided by 4, and then that's going to give us a measure of one central angle. That measure is going to be 90 because 36 divided by 4 is 9. Specifically, 360 divided by 4 is 90. And if you think back to when we talked about quadrilaterals, specifically squares, we learned that when the two diagonals of a square and the two diagonals of this square are in blue, we learned that when the two diagonals of the square intersect, they create a 90-degree angle. And ta-da! Here it is again. It's not contradicting what we learned before. So a 90-degree angle all the way around. Okay, so that's how you do that question. Central angle of each inside triangle. We are going to use this information to go a step further. So here is the next step. Given a regular quadrilateral, which we know is a square, with the radius of 4 radical 2. So I'm going to put that the radius, which means from the center to the vertex, so this part in blue, that length is 4 radical 2. Find the perimeter, apothem, and area. Okay, so it's asking us for a little bit more. It's asking us to find the perimeter, the apothem. And then notice how those two things are going to help us find the area of the square. So again, just to start off, because we know the radius, that can help us with finding the apothem and the perimeter. And just a reminder, this square is inscribed in this circle. So using that, we can figure out what the measure of each central angle is. And I'm going to do the central angle in green. So again, we do 360 divided by 4 because there are 4 congruent angles, and that's 90. And so that came from the example before. So this part right here is 90. This is 90, 90, 90, 90. In fact, all these radii right here in blue are 4 radical 2. All of them. So this is 4 radical 2, 4 radical 2, 4 radical 2, and 4 radical 2. However, I'm only going to focus in on one of them. So on 2 of them specifically. I'm only going to focus on this one and this one over here. Okay? Because we are going to use this triangle right here to help us find the apothem. And we'll go over it now. So I'm going to go ahead and draw in the apothem. And because I drew in the apothem, the one in red. We know that this is a right angle, because the height or the altitude of an object is always perpendicular to the base. I could have also drawn in this apothem over here, and now the base is this side, and then it would be, the apothem would be perpendicular. Again, I could have also drawn it up here, but we do not need to, because as stated earlier, the apothem, all these four apothems are going to be congruent. Here's the fourth one, but we do not need it. So we're only going to focus on this bottom one for now. So I'm going to erase the other ones just so that we have less clutter. Okay. And specifically because this triangle right here, the two radii and the side, think about what we know about this triangle here. A triangle that has two congruent sides, and we know that this triangle has two congruent sides because the sides in blue are the radii. This is an isosceles triangle, so that means that this point at the bottom is cutting this side at the bottom in half. So that means that this side from this vertex to this point is congruent to this side from this point to this vertex. So in other words, this point is the midpoint of this triangle here. And that's going to help us. Okay, half of 90 degrees. Remember, this whole angle was 90 degrees. And we figured that out earlier. 360 divided by 4 gave us 90. So half of 90, that means that this is 45. Okay, so this is 45. And then look at what we have. We have a 45, 90 plus 45 triangle. Or in other words, we have a 45, 45, 90 triangle. So that's going to help us find the apothem. And then that's also going to help us find this part of the triangle, which will then help us find the whole side. Okay, so let's go ahead and continue. So we know that a 45, 45, 90, I'm going to go ahead and copy it and then move it over so that we can review 45, 45, 90. And I hope that by now you're a little bit more familiar with a 45, 45, 90. All right, so with a 45, 45, 90, we know that the pattern is a number of x across the 45, the same number of x across the other 45, and then across the 90, we have that same number times radical 2. So here we can see that across the 90, we have 4 radical 2. So that means that x is 4. So that means that this side right here, this side is 4. So across the 45 is 4. So this length from the vertex to here is 4. Okay, and we also know that this side is also 4. So the apothem, I'm going to do the apothem in red. The apothem is actually 4 as well. All right, so we found the apothem. The apothem is 4. Now we need to find the perimeter. And I will do the perimeter, let's see, in purple. So the perimeter. So the nice thing is that the perimeter, I'm going to go ahead and erase the circle. Okay, so I'm going to remove it so that there's less clutter. I'm also going to remove this 90-degree angle so that there's less clutter. I'm going to remove these 45 so that there's less clutter. Essentially, I'm just cleaning it up so that there's less clutter. Okay, so we know that the perimeter is all the way around. So we talked about it earlier that because this point is the midpoint, we know that the distance from here to here is also 4. So we should have another 4. Okay, so now that's going to give us the length of one side of the square. Okay, and the length of one side of the square, 4 plus 4 is 8. All right, because we know it's a regular quadrilateral, we can figure out the perimeter. So the perimeter is going to be 8 plus 8 plus 8 plus 8. Or repeated addition is multiplication. So 8 times 4 is 32. All right, we're almost done. So the area, remember, is perimeter times apothem. So perimeter is 32 times apothem. And then we are going to divide the whole thing by 2. And again, if you're wondering why we divide by 2, please feel free to look at the video from before as to why we divide by 2. Okay, let's do some algebra. 32 times 4 will give us a large number. So let's try 32 divided by 2. So half of 32, think about what that's going to be. That's going to be 16. And then this is going to turn into a 1. All right, so now we have 16 times 4, which is a little bit more doable than 32 times 4. So think about what 16 times 4 is, and that's going to give us 64 units squared. So the area of this regular shape, which is a regular quadrilateral, is 64 units squared. So there you go. We're done with all 3 things. So that's the type of example that you might see where the apothem and the perimeter are not given to you right away. Okay. Here's a meme. Just peeked outside to see if it was hot. That's me right now, currently looking at the weather. But I'm glad it's hot. All right, let's try a couple more. I'm going to check how long the video is so far, because again, I like to keep them under 30 or close to 30 minutes. Okay, so given the regular hexagon, find the central angle of each inside triangle. So again, central angle of each inside triangle. You don't see any triangles, but we know if we draw the radii, which means you just draw lines from vertex to vertex, right? Vertices that are across from each other. That's essentially you drawing all radii. So there should be, because this is a hexagon, hex means 6, there should be 6 radii. Radii 1, 2, 3, 4, 5, 6. That's how you always tell. You always want to make sure you go to the corner. You do not want to go to a random point on the side. All right, so because it's a regular polygon, we know that each central angle is congruent. So what we're going to do is, to find the measure of each one, we're going to do 360 divided by 6, not 4 anymore. We're always dividing by the number of angles that we have. And we have 1, 2, 3, 4, 5, 6. I'll give you a hint. It's always divided by the number of sides of the polygon. So last time it was divided by 4 because there's 4 sides, and that's how we got 90 for each one. Okay, so the measure of each one is going to be 60 degrees. So this is a 60-degree angle. 60 plus 60 plus 60 plus 60 plus 60 plus 60. Okay, we're going to use this for the next question. The perimeter of a regular hexagon is 12. That's important. Find the radius. Let me color code. The perimeter is in blue, right? Blue. The radius is in black. And the apothem, I'm going to do it in red. Okay. And then the area. So what we're going to start off by doing is we're going to put everything that we know on the diagram. So we know that the perimeter is 12. More specifically, think about what the length of each side is going to be, since this is a regular polygon, regular hexagon. So you're correct. That's 12 divided by 6. So 12 divided by 6 sides is 2. So 2 all the way around. Okay, I'm not going to write it in for each triangle, but it's just 2, 2, 2, 2 all the way around. Okay. And we also know one additional thing. We know that this central angle is 60 degrees. So I'm going to put it on this triangle, 60 degrees, even though we know that this is also 60, 60, 60, 60, 60. Why? Because we just did that on the last question. 360 divided by 6 is 60 degrees. Okay, now what we're going to do is we're going to take this triangle here at the bottom that's created by the two radii and the side, one side. We are going to draw the apothem of that triangle. Remember, apothem is just the height of that one triangle. We could draw it in for this one as well, but it's always easier to work with one that has a horizontal base. We know that this is the midpoint of this bottom side. Okay, and remember, we have a 60-degree angle here, and because we drew in the apothem, we're taking that 60-degree angle and cutting it in half. So that 60-degree angle will turn into a 30. So this is going to be 30. This is also going to be 30. But we're just going to focus on this triangle right here, the one on the left. I know we have so many triangles. So now we're focusing on this one, the 30, 90, 60 triangle. And look at that. We have a 30, 60, 30, 60, 90 triangle. So we are going to use our knowledge that we have on 30, 60, 90. So I'm going to draw the triangle on the left. And then I'm going to move it over so that we can focus on that one, make it a little bit larger. And that's going to help us find for other things. So let's put in what we know. So we know that this is 90. We know that this is 60. Okay. We also know that this whole side, the whole side is 2. And we know that this distance from here to here is half of 2, which is reflected over here. So that's going to be 1, 1. Okay. Now, if you remember the pattern for a 30, 60, 90, so I'm going to draw it over here. The pattern for a 30, 60, 90, I'm going to put 60 here. You can barely tell that should be 60 right here. Okay, so across the 30, we have a number. Across the 60, we have the same number times radical 3. Boom. That's what we have. And then across the 90, we have twice of that number. Okay, so here we know that across the 30, we have x. So across the 30, we have 1. So across the 60, this should be 1 radical 3. 1 radical 3. And ta-da, that is reflected over here. It's the apothem. So the apothem is 1 times radical 3. Okay, so that we're done with that. Check. All right, radius. We want to know what the radius is in black. So across the 90-degree angle should be twice of this number, which should be 2. Okay, 2. So the radius is 2. So the distance from this vertex to the center is 2. Boom, we're done with the radius. All right, now we just need to find the area. So for the area, I'm going to do that one in purple. Area is perimeter. And the perimeter we know is 12. So it's kind of neat because we don't need to calculate the perimeter since it gave it to us here at the top, times the apothem. And the apothem is in red, which we found to be 1 radical 3, times 1 radical 3 divided by 2. Okay, so let's do our algebra. 12 divided by 2, that's going to be 6 over 1. 6 times 1 is 6 radical 3. So the area is 6, so equals 6 times radical 3. Units squared. And that is it. Okay, so if you remember when we constructed a regular hexagon, I had you make 6 equilateral triangles. Equilateral triangle 1, 2, 3, 4, 5, 6. So it makes sense that when we draw in the apothem for one equilateral triangle, this is going to turn into a 30, 60, 90 because we talked about it when we learned 30, 60, 90. 30, 60, 90 triangles come from an equilateral triangle that's been cut in half. Mind blown. So nothing again contradicts each other. So that's a little bit more kind of tying what we've been learning to what we're currently learning. Okay. All right. Let's see. I'm going to show you one more. This one's going to be a really challenge question. Challenge. It's going to be tough, but I want you to hang in there. Okay. So we're going to try it together. Find the area of a regular octagon with a side length of 10. Okay. So feel free to pause the video, figure out what you need to find. Feel free to look back in the video, and then feel free to come back here. This is going to be the last thing that we do. All right. Let's go ahead and try it all together. So we know that the side length is 10. So 10 all the way around. Octagon, like an octopus, has 8 sides. Okay, so it's going to be 10, 10, 10, 10. So the perimeter, we can already find the perimeter. Okay, so let's fill in what we know. Perimeter is going to be 80. Now think about what else we need to know for the area formula, because we need to know the area. Well, for the area, we need to know the apothem. So A, lowercase a, is apothem. We need to know that. We don't know what it is. So we need to figure out the apothem. So what I'm going to do is I'm going to draw the radius of, I'm going to use a line to be a little bit more exact. I'm going to draw the radii. So I'm going to draw in all the radii. So I'm going to go from the center to the vertex. And that's going to help me find the radius. Okay. So think about how many triangles inside we're going to have. And it should be 8 because we have 8 sides. So let's count them. 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 triangles. So now what we need to do is we need to figure out the apothem. And the apothem, I'm going to go ahead and draw in red. So we need to figure out what that length is. Okay. Again, you can always draw it over here as well. It's just easier to work with a side that is horizontal rather than diagonal. So I'm going to work with this bottom side. Okay. I'm going to erase that apothem. So we need to find this, but we need a little bit more information. Specifically, we need to know what the central angle is. So we need to know what the measure of one central angle is. So that's going to be 360 divided by not 4, not 6 anymore, divided by 8, because we have an octagon, and an octagon has 8 sides. And again, just a reminder for those of you that do not have a calculator, you know my favorite tool, Decimal's calculator. So I'm going to put it over here. 360 divided by 8, 45. Boom. So we know that this angle right here is 45. All right. That's great because it's going to help us find the apothem. Okay. So once we found the center angle, we know that this angle over here of 45 degrees is cut in half when we draw the apothem. So when we draw the apothem, we need to know what this angle is right here, the very tiny one. So think about what's half of 45. And it's going to be 22.5. So we know I'm going to go ahead and do the following. I'm going to trace this triangle and make it larger. So I'm tracing this triangle on the left, and I'm going to make it larger, just so that we can write inside the triangle. Stay with me. We're almost done. Don't leave yet. Okay. So we know the following. We know that half of 10 is 5. So this is 5. Since this is the apothem over here, this is the right angle. Okay, so And we also know that this center angle of 45 got cut into half, so 22.5. All right, so here is the issue. This triangle does not create a 30, 60, 90, nor does it create a 45, 45, 90, nor do we have two sides that we can use to solve for the apothem. So we cannot use the Pythagorean theorem. We cannot use special right triangles. However, we can use sine, cosine, or tangent. We can use sine, cosine, or tangent to solve for the apothem. So think about it in your head. Right now we have this angle right here. Think about which trig ratio uses opposite and adjacent. That is not sine. Sine is opposite over the hypotenuse. We do not want to know what the radius is. Notice how this is a hypotenuse. We do not need the radius for this one because it's asking us just for the area. So the radius is not going to help. Cosine of 22.5 is apothem or adjacent side divided by the hypotenuse. Notice how we do not know the apothem. Notice how we do not know the hypotenuse. So we have two unknowns. That is not going to help us. We want to use tangent. I'm going to write that one in black. So tangent of 22.5. Hopefully we did not forget what this is. Tangent of 22.5 equals opposite, which is 5, divided by the apothem. And here A stands for apothem, not necessarily adjacent, even though it is the adjacent side of 22.5, the angle 22.5. Okay, we're going to go ahead and cross multiply. Remember, I like to put this over 1. Cross multiply, then you end up getting the following. It's going to take me a little bit, so we're going to end up getting A times tangent of 22.5. So A times that, I'm going to move it a little bit more, equals 5, okay? And because all it is 1 times 5. Okay, last thing we need to do is we need to divide both sides by tangent of 22.5. So the apothem equals 5. I'm gonna use the decimals calculator. 5 divided by tangent of 22.5. Okay, so we're gonna approximate to 2 digits after the decimal. So this stays as a 7. So 12.07. So the apothem is 12.07. All of that hard work for the apothem. So this is why it's so important for you to really understand trigonometry, which is what we talked about with right triangles. Okay, I'm going to go ahead and clean this up. I'm going to erase this because we do not need it. I'm going to go ahead and bump this up just so you can understand the ratio and then the algebra. All right, and now we have the apothem. So I'm going to go ahead and also put it up here. And then now we have everything. We have the perimeter and the apothem to find the area of the regular octagon. Okay, so again, this triangle helped us solve for the apothem, and this triangle came from here. I just made it larger. Okay, so I'm gonna do it in black for the area. So the area equals apothem times the perimeter. So I'm going to copy and paste. Here's the perimeter. I guess I cannot. The perimeter is 80. And again, we got that because we knew that each side of length was 10. So 10 times 8 times the apothem. And we got that using trigonometry. And that's going to be divided by 2. Now, I do not expect you to do that by hand, but we can do part of it by hand. I'm going to make this a little bit smaller, okay? Just so that we can make some space. I do not expect you to do that by hand, but you can try. So what I'm going to try first is, 80 divided by 2, that's pretty doable. I know that's going to be 40. So technically this is 40 times 12.07. I'm going to go back to decimals. I'm going to go ahead and do 12.07 times 40 because 80 divided by 2 is 40. All right, so the area is this valley, 482.8 units. So that is the area of this regular octagon. Okay, so again, this was a challenging question. So now you kind of have an idea more of how to do those questions that do not give you the apothem or the perimeter right away. You have to do a little bit of work. All right, everybody, thank you for tuning in. Thank you for staying resilient and hanging in there. Feel free to contact me if you have any questions. Have a good rest of your day.